So, hi there. My name is Henrik Petersson, and I am a PhD student at the Division of Solid Mechanics at Linköping University. And I will talk about some physics-informed modeling for stress and fatigue, and some safety factors for that part. So we start off by looking at some experimental data. We have the stresses here and the cycles to fatigue here, and we have our data. We have some runouts, and usually what we do is that we do an isostandard regression, which is a linear regression in the log-log diagram. The question that you can ask is, what about, we have some kind of fatigue limit for this material. This is a normal steel. Not all have a straight line for fatigue limits, perhaps some sloping, but here we have the assumption that we have a fatigue limit. And we have some kind of upper limit. We have the yield stress for that part. For the modeling of this part, we can simplify it by having the cycles to fatigue as this function is how we describe the curve depending on the stresses. And then we have our deviation from our experimental data that we're having. So for the first part, we're looking at this regression line or the modeling. Here we will use a neural network, which is, we have our input. In this case, we have the stresses. We feed it through the network. We will have our output, which is the cycles to fatigue. We then update our losses, and then we feed it backwards into the network and update it until we reach a certain amount of loss, which we are fine with. By doing this, we will end up with something like this. So we have very good checking out all the experimental data, but extrapolation is really, really bad outside of this regression. So what do we know? We know that we have some kind of linear behavior in the log-log diagram. So we look at our neural network again, and then we implement this part. So we start looking at some physics or mathematics that we can incorporate into our loss function. So this loss function acts then in the same region for this part. So we're looking at, we have our log-log for the cycles and our stresses. We have our model parameters that is also set in the neural network. They will also be updated during the training sequence. And by doing this, we know we have some function here that is also minimized during the training sequence. So when we incorporate this, then we're starting to have very similar behavior as this ISO standard. So now we can use this model to extrapolate outside it. But at the same time, we would like to capture these parts. So how do we do that? Well, we just basically incorporate it into the loss function again. So here we have a description of the behavior of our stress limit, and here the fatigue limit. And this whole part is then described as a physical loss. And by doing this, we then, for this part, we're capturing the stress limit. And for here, this part, we're capturing the fatigue limit. So here we have a regression function now, a model that's capturing the whole behavior. And it also continues this function. So very nice to have. So now we are capturing our fatigue model. And we want to look at the error part now. And for this part, we're turning to statistics. And what we do is we assume a Gaussian distribution for this scatter, this deviation for this model. And for the standard deviation, we're using the Gaussian kernel function. So we have a description of how the data deviates from our model. And by doing this, we can have this variety of safety factors during the whole regression. So we end up with a 95% probability interval, and capturing all this scatter, we can see that we have a smaller band right over here where we have a lot of points, and then we have increased scatter over where we have lesser points. So we're increasing the safety factor where we know less. And when we compare it against this, as I call ISO standard, if we have that probability interval for that part, which is dotted here, we can see that we'll have, at one place, we can have a 28% better life without increasing the risk of failure. So while down here, we will have very similar. So at some point where we have a lot of data, we can increase the cyclic life in sense of not increasing the risk. Then we started looking at what happens if we removing points. We would like to increase the risk, so we would like to describe this behavior or implement something that could capture this. So one thing is that you can look at in the Gaussian kernel function, you will have this H parameter, which is a hyperparameter, so you can tune it to whatever you want. So you can increase that one to smoothing the curve for safety factors. Or you can implement a bit more complicated function, which is dependent on the distance. So it's not the kernel function, but similar, you can say. So then we will have a widening band here for these parts where we're missing data points, and we'll get an increased where we're extrapolating our data. So we can manipulate the safety factors as we also would like, but still we're taking the known data into account. So the further away we are from our known data, the more increase we will have in the safety factor. So for the conclusion for this work is that managed to create a physics-informed neural network for the modeling that captures our wanted behavior. And we have estimated the error in a way that can decrease our risks, decrease our safety factors without increasing the risk. And for our future work is that we would like to have some kind of scatter band also for the fatigue limit and stress limit, but right now the mathematics is a bit in the way, so it goes towards the physics-informed model. So that part is still ongoing, and then we would like to implement some temperature influence. So that was what I was planned to go through. Went a bit quick, but thank you.